half of the universe's normal material has vanished from our accounting. This is not about dark matter or dark energy, but the very atoms that build stars, planets, and you. Cosmologists call this the Missing Baryon Problem, a cosmic inventory mystery where the books simply do not balance. Baryons are the protons and neutrons that make up everything we see and touch. Yet when we tally what should be here from the universe's birth and what we actually find in galaxies today, a staggering 50% is missing. By the end of this, you will have a front row seat to the greatest detective story in modern astronomy, equipped with 25 clues that are finally closing the case. Where could half of creation be hiding? And what does its discovery reveal about the hidden skeleton of the cosmos? The search takes us from the afterglow of the Big Bang to vast oceans of gas hotter than 1,000,000 suns. What do you think it means to find something that has been invisible since the beginning of time? The case begins with a simple ledger, a cosmic inventory taken at two very different moments in time. Our first piece of evidence comes from the oldest light in existence, the cosmic microwave background. This faint afterglow, a snapshot of the universe when it was just 381 years old, acts like a fossilized record. By studying its subtle patterns, cosmologists can count with incredible precision how many protons and neutrons, how much normal matter, existed at the dawn of everything. It is a firm, foundational number, the universe's starting capital. Now, fast forward nearly 14 billion years. Astronomers turn their telescopes to the universe we see today, tallying all the baryons they can find locked inside stars, swirling in galaxies, and floating as cold gas in the vast spaces between them. The result is a staggering shortfall. When you compare the ledger from the beginning to the ledger of the present, over half of the original normal matter is simply gone from the accounts. It is not a small accounting error. It is a gaping hole in our cosmic census. This is clue number one, the cosmic census discrepancy. Visualize a pie chart representing all the normal matter from the early universe. A massive slice, more than 50%, is simply blank, labeled missing. This missing material is not the mysterious dark matter. It is the ordinary atoms, the building blocks of everything familiar, that have somehow vanished from plain sight. The universe wrote a check with its birth, but by the time we came to cash it, half the funds had disappeared. Where did they go? The blank slice in that cosmic pie chart is not truly empty. It is filled with our prime suspect, a ghostly medium so elusive it has evaded detection for decades. This is clue number two, the warm-hot intergalactic medium, or WHIM. Picture the grand structure of the universe not as isolated islands of galaxies in a dark sea, but as a vast, intricate spiderweb. Galaxies cluster at the intersections of the threads, but the threads themselves, stretching across billions of light years, are theorized to be conduits of unimaginably hot gas. This is the WHIM, a diffuse fog of matter heated to temperatures between hundreds of thousands and millions of degrees. At such extremes, the gas does not glow in visible light our eyes or standard telescopes can see. It becomes almost perfectly transparent, a cosmic stealth material. This is precisely why it has remained hidden. Traditional astronomy looks for stars, for cold clouds of gas that absorb light, or for blazing quasars. It is ill-equipped to see something that is both incredibly hot and incredibly thin, like trying to spot a wisp of steam in a blast furnace by looking for a shadow. Yet, according to sophisticated supercomputer simulations of cosmic evolution, this filamentary web should contain the overwhelming majority of the universe's normal matter. It is not in the galaxies themselves, but in the scaffolding that connects them, the hidden plumbing system of the cosmos where the water, the very atoms of creation, continuously flow. If these models are correct, then the missing baryons are not missing at all. They are right in front of us, woven into the fabric of space, simply waiting for us to learn how to see them. But how do you see a ghost? You need the right kind of eyes. To hunt for a medium of gas heated to millions of degrees, astronomers had to shift their vision entirely, moving from the optical light we see to the high-energy realm of X-rays. This is clue number 3, X-ray eyes on the sky. At those staggering temperatures, atoms are violently stripped of their electrons, creating a seething plasma that glows not in visible colors, but in X-rays. It is a fundamental signature, like the thermal radiation from a blast furnace. To capture this faint whisper from the cosmic web, we needed observatories that could operate above our protective atmosphere, which thankfully blocks these dangerous rays from reaching the ground. Enter the great X-ray hunters, telescopes like NASA Chandra X-ray Observatory and the European Space Agency's XMM Newton. Launched around the turn of the millennium, these instruments were our first real chance to scan the heavens for the predicted glow of the WHIM. The challenge was immense. We were not looking for bright, point-like sources, but for an incredibly faint, diffuse haze spread across vast stretches of nothingness. It is akin to trying to detect the heat signature of a single candle held miles away, while standing in front of a roaring bonfire. The cosmic background itself is noisy with X-rays from other sources. Early successes came from looking at dense knots in the web, where the signal would be strongest. Observations of massive galaxy clusters, the universe's great cities, revealed they were immersed in colossal halos of this million-degree gas, far exceeding the mass of all the stars within the galaxies themselves. These halos were the first direct evidence that a huge reservoir of hot baryons existed outside of galaxies. They were the dripping faucets that hinted at the existence of a vast, hidden plumbing system. Finding these halos was a crucial step, proving the models were pointing in the right direction and that the tools we had could, in principle, find the missing material. But the true filaments, the thin threads of the web themselves, remain just beyond our grasp, their signal too subtle to pull from the noise. The hunt was on, but the ghost was still winning at hide and seek. The ghost was hiding in plain sight, but we needed to read its shadow. Another brilliant method emerged, one that did not look for the hot gas itself, but for the subtle fingerprint it left on the oldest light in the cosmos. This is clue number 4, the Sunyaev-Zel'dovich effect. Picture the cosmic microwave background, that ancient afterglow from the infant universe, as a smooth, cold sea of light bathing all of space. Now, imagine a massive cloud of incredibly hot gas, like the halo surrounding a galaxy cluster, sitting directly in the path of this light. As the CMB photons, those ancient particles of light, travel through this seething cloud, they occasionally collide with the high-energy electrons whizzing around. These collisions give the photons a tiny kick, a slight boost in energy. It is like a ping-pong ball being hit by a speeding tennis ball. The ping-pong ball gets a jolt of energy and flies off faster. This interaction leaves a distinct, cold shadow in the precise microwave frequencies of the CMB. The region behind the hot gas cloud appears ever so slightly dimmer at its original, cooler frequency, because those photons got boosted up to a higher energy band. It is an incredibly subtle distortion, a whisper of a shadow, but it is a direct and powerful signature. The beauty of this effect is that it does not depend on distance. Whether the galaxy cluster is relatively nearby or extremely far away, the strength of the shadow imprint remains the same. making it a perfect tool for surveying the universe on the largest scales. Major projects like the European Space Agency's Planck satellite and ground-based observatories like the Atacama Cosmology Telescope in Chile have spent years meticulously mapping the entire sky for these minute distortions. Their results have been nothing short of revolutionary, painting a detailed census of where hot gas resides. These surveys have confirmed that colossal reservoirs of million-degree plasma are not rare anomalies but a fundamental feature of the cosmic landscape, enveloping galaxy clusters and, crucially, tracing the faint outlines of the connecting filaments between them. Each cold shadow on the ancient light is a receipt, proof of payment that the universe's hot gas is there, woven into the very structure of reality. We were no longer just theorizing about the hidden plumbing. We were starting to see the outlines of the pipes etched onto the sky itself. Yet another method emerged, one that turned the universe's brightest beacons into precision searchlights. Brilliant quasars, the cores of distant galaxies powered by voracious supermassive black holes, shine with an intensity that can outshine entire galaxies. Their light travels for billions of years across the cosmos to reach us. Astronomers realized they could use these quasars as cosmic backlights. If the light from a quasar passes through a filament of the warm, hot intergalactic medium on its long journey, the specific atoms within that hot gas should leave a fingerprint. This is clue number 5, absorption lines in quasar spectra. The process is akin to holding a prism up to a pure white light. The prism spreads the light into a full rainbow spectrum, a continuous band of color. Now, if you pass that light through a specific gas, say neon, the neon atoms will absorb very specific, narrow slices of that rainbow, creating dark lines in the spectrum at wavelengths unique to neon. For the WHIM, the key atoms are highly ionized oxygen that has been stripped of most of its electrons by the intense heat. When quasar light passes through a filament of this million-degree plasma, these oxygen ions snatch away very specific, precise wavelengths of light. The result is a series of extremely faint, dark absorption lines etched into the quasar's otherwise smooth spectrum. Finding these lines is a monumental challenge. The filaments are so diffuse that the absorption lines are incredibly shallow, mere whispers of shadow on an already complex signal. It requires combining the light from many quasars, looking for the same telltale lines at the same precise wavelengths, to build up a statistical signal. It is like listening for a single, faint note played by an invisible flute in a roaring symphony hall. But when astronomers succeed, they are not just detecting hot gas. They are taking its temperature, measuring its density, and even mapping its velocity. Each absorption line is a direct chemical signature, a confession from the missing baryons themselves, stating exactly what they are and where they are hiding. This shadow puppet method has provided some of the most compelling, direct evidence that the predicted filaments of the WHIM are real, and they are indeed threaded with the atoms we have been searching for all along. These faint absorption lines in quasar light are not random shadows. They are precise signatures, a chemical confession from the missing material itself. This brings us to clue 6, the specific fingerprints of O7 and O8. In the searing heat of the warm, hot intergalactic medium, where temperatures soar past 1,000,000 degrees, ordinary atoms do not survive intact. Take an oxygen atom, which normally has 8 electrons orbiting its nucleus. In this extreme environment, it is brutally stripped. O7 refers to oxygen that has lost 7 of its 8 electrons, leaving just 1 bound to the nucleus. O8 is oxygen stripped completely bare, a naked atomic nucleus. These highly ionized states are the unique calling cards of the WHIM. because only gas at these staggering temperatures can produce them in significant quantities. When the light from a distant quasar passes through a filament of this plasma, these oxygen ions act like microscopic filters. They absorb very specific, precise wavelengths of X-ray light, creating those telltale dark lines in the spectrum. Searching for these lines is the astronomical equivalent of forensic analysis, looking for a specific set of fingerprints at a cosmic crime scene. The challenge is that the signal is incredibly weak, a whisper almost drowned out by noise. But patience and precision have paid off. One landmark detection came from observations toward a brilliant quasar known as H1821 plus 643. Using the unparalleled sensitivity of the Chandra and XMM Newton observatories, astronomers stared at this beacon for a combined total of over 5 days, gathering every precious photon. In the resulting spectrum, they found it. The clear, though faint, absorption lines of 07 and 08 etched into the data. This was not a statistical hint or a theoretical prediction. It was a direct, unambiguous detection of the hot intergalactic medium in a relatively isolated filament of the cosmic web. It was the smoking gun. For the first time, we could point to a specific location in the vast emptiness between major galaxies and say with confidence, here it is. Here are the missing baryons. They are not in some exotic form, but are exactly what we predicted: ordinary atoms heated to an extraordinary state, caught in the act of absorbing the light from a distant beacon. This single detection validated decades of theory and proved that our methods for finding the ghost were finally sharp enough to see its face. The smoking gun detection of hot oxygen ions was a triumph, but it was also a single data point in an unimaginably vast cosmos. To find more of these ghosts, astronomers needed a treasure map. That map comes not from telescopes, but from the raw computational power of supercomputers, giving us clue 7, the cosmic web filaments in simulations. Inside these machines, physicists program the fundamental laws of the universe: gravity, the expansion of space, the behavior of dark matter and ordinary gas, and then press play on the story of creation. They start with a nearly smooth distribution of matter, a digital approximation of the early universe, and then let the simulation run for billions of virtual years. The results are breathtaking visualizations, a swirling dance of dark matter forming an intricate, three-dimensional spiderweb across the void. Bright knots form where the threads intersect, becoming the galaxy clusters and superclusters we observe. But the true revelation is in the threads themselves, the vast, delicate filaments that stretch across millions of light years. According to these simulations, this filamentary web is not just a skeleton of dark matter. It is also the primary reservoir for the universe's normal matter. The models predict that the majority of baryons, especially those heated to extreme temperatures, are not inside the galaxies. They are flowing through these immense cosmic arteries, the warm, hot intergalactic medium concentrated along the filament spines. Think of it like a global water system. Galaxies are the great cities clustered at river deltas or mountain springs, but the water that sustains them travels through a continent-spanning network of rivers, streams, and underground aquifers. For decades, we only saw the cities. The simulations showed us the blueprint for the entire hydrological network, predicting exactly where the water, the missing baryons, should be flowing. This digital map became the ultimate guide for observers. Instead of pointing telescopes randomly into the void, hoping to stumble upon a faint signal, they could now target the specific regions where the simulations said the filament should be strongest, the relatively straight lines between massive pairs of galaxy clusters. These supercomputer visions transformed the search from a blind hunt into a guided expedition, telling us precisely where to train our X-ray eyes and quasar backlights to have the best chance of catching the universe's hidden material in the act. Armed with that digital treasure map, astronomers needed a way to confirm its accuracy in the real universe. This required a survey of unprecedented scale, a project to chart the cosmos in 3 dimensions. That project is Clue 8, the Baryon Oscillation Spectroscopic Survey, or BOSS. Operating from the ground-based Sloan Foundation telescope, BOSS did not look for the faint WHIM directly. Instead, it performed a monumental census, meticulously measuring the precise positions and distances of over 1 million galaxies. This created the most detailed 3-dimensional map of the visible universe ever made at the time, a sprawling chart that revealed the large-scale cosmic web in stunning clarity. For the first time, we could see the predicted filaments not just in simulations, but etched across the real sky, with galaxies strung along them like luminous beads on invisible strings. With this real-world map in hand, the hunt for the missing baryons entered a new strategic phase. Astronomers could now take the light from not just 1 or 2 quasars, but from thousands of them, and cross-reference their positions with the BOSS map. They specifically selected quasars whose light, on its journey to Earth, was known to pass through one of these mapped cosmic web filaments. The individual signal from any single quasar sightline through a filament was still too faint to declare a definitive detection. But here, statistics became the ultimate amplifier. By stacking or combining the data from hundreds of quasar spectra, all aligned with these cosmic web threads, the incredibly faint absorption signatures of the WHIM, those whispers of highly ionized oxygen, began to add up. The random noise averaged out, and a clear, coherent signal emerged from the chaos. This statistical stacking technique was like using a chorus of distant flutes, all playing the same faint note, to finally hear the melody over the cosmic background roar. The result was a resounding confirmation. The boosted signal showed a definitive excess of absorption precisely correlated with the locations of the cosmic web filaments charted by BOSS. This was the proof that the missing baryons were not just floating randomly in the void. They were inextricably linked to the large-scale structure of the universe, concentrated along the very filaments that the simulations had predicted. The ghost had been cornered, and its hiding place was exactly where our digital models said it would be. The statistical chorus from BOSS confirmed the ghost's location, but we still needed to see its full form. Enter a revolutionary new pair of eyes in space, the extended R-Roentgen survey with an imaging telescope array, or eROSITA. This German-Russian X-ray observatory, launched in 2019, was designed for one monumental task: to perform the deepest, most complete all-sky survey ever in the soft X-ray band. Its wide field of view and exquisite sensitivity meant it could scan huge swaths of the sky with every glance, building up a panoramic map of the hot universe with unprecedented speed and detail. In its very first all-sky survey, eROSITA delivered a staggering surprise, not in some distant filament, but right here in our own galactic backyard. It revealed colossal, symmetrical structures erupting from the plane of the Milky Way, vast bubbles or immense hot gas filaments extending tens of thousands of light years above and below our galaxy. These eROSITA bubbles are a titanic echo of some ancient cataclysm, likely a period of frenzied activity from the supermassive black hole at our galaxy's center millions of years ago. Their discovery was shocking, but for our search, they serve as a powerful proof of concept. They show that E-Reseda can see the faint, diffuse glow of million-degree gas on the largest scales, gas that was completely invisible to previous telescopes. This capability is now being turned on the cosmic web itself. As E-Reseda continues its scans, it is not just looking at bright clusters, it is performing a systematic census, weighing the hot gas in the seemingly empty regions between galaxies. It is directly measuring the density and distribution of the warm-hot intergalactic medium across our local universe, providing the first truly comprehensive accounting of this hidden component. Think of previous X-ray telescopes as powerful spotlights, illuminating one small, bright area at a time. E-Reseda is like turning on the stadium lights for the entire cosmic arena, revealing not just the players on the field, but the very atmosphere filling the stadium. With each new scan, it is adding hard numbers to our ledger, directly weighing the ghostly filaments and finally telling us, in precise terms, how much of the missing 50% is right there, woven into the hot fabric of space. The case is not just about finding the missing baryons anymore. It is about taking their official portrait and measuring their exact mass. These new cosmic flashlights are not the only tools illuminating the darkness. A different kind of signal, one of the most mysterious in all of astronomy, is now proving to be a perfect probe for the hidden seas of gas. This is Clue 10, fast radio bursts as cosmic dipsticks. Fast radio bursts, or FRB, are exactly what their name suggests, flashes of radio waves that last for mere thousandths of a second. Yet in that instant, they release as much energy as our sun does in 80 years. They come from distant galaxies, billions of light years away, and their origins are still a thrilling puzzle involving magnetars or cosmic collisions. But for our search, it is not their source that matters most. It is their journey. As these incredibly brief radio signals race across the universe, they do not travel through a perfect vacuum. They pass through the diffuse plasma of the warm, hot intergalactic medium, the very hot gas we are trying to weigh. Inside this plasma are free electrons, particles unbound from their atoms. When the radio waves encounter these electrons, a fascinating thing happens. The different frequencies of the burst are slowed down by slightly different amounts. Higher frequency waves travel just a bit faster than the lower ones. This causes the signal to spread out or disperse during its long voyage. It is similar to how a prism spreads white light into a rainbow, but in time rather than space. By the time the burst reaches our telescopes, its sharp millisecond ping has been smeared into a distinctive descending chirp. The crucial insight is that the amount of this dispersion is directly proportional to the total number of free electrons the signal encountered along its path. More electrons mean more spreading. Think of it like a dipstick used to check the oil level in a car's engine. The length of the oil smear on the stick tells you how much oil is in the pan. In the same way, the amount of dispersion in a fast radio burst tells astronomers the total column density of ionized gas it traveled through. Each burst provides a single, integrated measurement, a total sum of all the hot electrons in the cosmic web between its host galaxy and Earth. This makes FRBs phenomenal tools for cosmic accounting. While quasar absorption lines give us a detailed chemical fingerprint at one specific point, a fast radio burst gives us the grand total for the entire journey. When astronomers collect enough bursts from different directions and distances, they can begin to build a three-dimensional map of the WHIM density throughout cosmic history. Early results from surveys like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, are already aligning with predictions. suggesting that the amount of diffuse gas they measure could account for a significant portion of the missing baryons. These mysterious flashes, once just cosmic curiosities, have become one of our most precise tools for taking the measure of the invisible universe, one brilliant millisecond chirp at a time. The universe writes its history in light, and we have learned to read its many dialects. One of the most eloquent is the Lyman alpha forest, a beautiful phenomenon seen in the optical spectra of distant quasars. As a quasar's ultraviolet light journeys through space, clouds of relatively cool, neutral hydrogen gas absorb very specific wavelengths, creating a dense thicket of dark absorption lines. Each line is a snapshot of a single hydrogen cloud at a specific distance. This forest has taught us volumes about the cosmic distribution of cooler gas. But it only tells half the story. For the hotter, ionized material of the WHIM, we must listen to a different, far more subtle dialect. This is clue 11, the Lyman alpha forest and its hot cousin, the X-ray forest. The principle is similar, but the signature is transformed by temperature. Instead of neutral hydrogen absorbing ultraviolet light, we search for highly ionized metals like oxygen and neon absorbing X-rays. The resulting pattern is an X-ray forest, a sparse and faint collection of absorption lines from gas heated to millions of degrees. Comparing the two forests is like comparing a detailed map of a continent's rivers and lakes with a thermal satellite image showing underground geothermal currents. One reveals the visible, cooler waterways. The other unveils the hidden, seething heat beneath the surface. They are complementary records of the same cosmic geography. By analyzing the same quasar sightline with both optical telescopes for the Lyman alpha forest and X-ray observatories for the faint X-ray lines, astronomers can perform a full thermodynamic scan of a cosmic filament. They can see where the cooler gas ends and the superheated plasma begins, mapping the transition zones and understanding how these different phases of matter interact and coexist within the web's architecture. This combined approach is powerful because it proves the missing baryons are not in a single, simple state. They exist in a complex ecosystem of temperatures and densities, from lukewarm hydrogen clouds to blazing oxygen plasma, all tracing the same invisible threads of the cosmic web. The story is no longer about finding one missing component, but about understanding the full, dynamic life cycle of ordinary matter as it flows through the grand structure of the universe. The cosmic web did not form in silence. Its vast reservoirs of hot gas were filled by titanic explosions, the very engines that shape galactic destiny. This is Clue 12, Galactic Winds and Feedback, the story of how the baryons were violently evicted from their homes and pushed into the intergalactic void. For decades, we viewed galaxies as isolated islands, quietly converting their gas into stars. But reality is far more dramatic. Galaxies are dynamic ecosystems, and their most energetic events act like colossal pumps, spewing matter back into space. Two primary forces drive this exodus. The first is the collective fury of supernova. In regions of intense star formation, called starbursts, massive stars are born, live brief, brilliant lives, and die in catastrophic explosions. Thousands of these supernovae can detonate in quick succession, their combined shock waves blowing a hurricane of hot gas and heavy elements clear out of the galaxy's disk. The second, even more powerful force comes from the galaxy's heart. When a supermassive black hole actively feeds, it becomes an active galactic nucleus, a quasar. The incredible energy released can drive bipolar jets and outflows that literally blow bubbles in the surrounding gas, ejecting material at velocities that can reach a significant fraction of the speed of light. To see this process in action, look no further than the galaxy Messier 82, a classic starburst galaxy. In stunning telescopic images, you do not just see a disk of stars. You see colossal plumes of reddish gas erupting perpendicularly from its center, stretching for tens of thousands of light years. These are not gentle breezes. They are a galactic superstorm, a visible testament to the raw power of stellar feedback, hurling the very ingredients for future stars and planets out into the cosmic wilderness. This ejected material does not simply vanish. It travels vast distances, eventually slowing and mixing with the primordial gas that already exists in the spaces between galaxies. It enriches that medium with heavier elements forged in stellar cores and supernovae. And, crucially, it adds its mass to the diffuse pools of the warm, hot intergalactic medium. The galactic winds are the delivery system, answering the crucial question of how the baryons got into the filaments in the first place. They are the great migration event of the cosmos, where galaxies, through their own furious cycles of birth and death, continuously seed the web that binds them together. The missing baryons are not lost. They were exiled, cast out by the very stellar fires that gave their homes light, now destined to drift in the hot darkness between the stars. This galactic exodus does not end in the vast intergalactic wilderness immediately. The ejected material first enters a dense, complex frontier region surrounding every galaxy, a place known as the circumgalactic medium. This CGM is a massive, multi-phase halo of gas, dust, and plasma that envelops galaxies like our own Milky Way, extending for hundreds of thousands of light years. It is a bustling cosmic port, a place of constant arrival and departure. Here, the hot winds from supernova and black holes first deposit their cargo. Cooler gas from the intergalactic medium also funnels in along the cosmic web, drawn by the galaxy's gravity, potentially to fuel future generations of stars. The circumgalactic medium is a dynamic buffer zone, a reservoir of baryons that is neither truly inside the galaxy nor completely free in intergalactic space. It blurs the boundary completely. Observations from the Hubble Space Telescope have been pivotal in mapping this elusive region. By using the light from distant quasars as backlights, just as we do for the distant WHIM, Hubble has detected the absorption signatures of this circumgalactic fog around countless galaxies. It sees not just hot gas, but warm and cool clouds, all swirling in a complex ecosystem. This halo contains a staggering amount of mass, potentially equaling or even exceeding all the visible stars within the galaxy itself. For our cosmic ledger, the CGM represents a major, previously overlooked column. A significant portion of the so-called missing baryons are not in the far-flung filaments, but right here in the extended atmosphere of galaxies, a vast and hidden ocean we have only just begun to chart. It is the galaxy's own long-term storage, a repository for its past eruptions and a potential pantry for its future growth, making the line between a galaxy and the cosmic web fainter than we ever imagined. Our galaxy's own circumgalactic halo is just one layer of a much larger local structure. This brings the mystery home with Clue 14, the missing baryons in our own cosmic backyard. Astronomers have performed a remarkably detailed audit, measuring all the normal matter they can find within a sphere about 1 billion light years across centered on our Milky Way. They tally the stars in every galaxy, the cold gas in their disks, the hot plasma in galaxy clusters, and the diffuse glow from our own circumgalactic medium. It is the most complete local inventory possible. Yet, when they compare this total to the amount of primordial baryons that should be here based on the cosmic microwave background, a familiar gap appears. Even in our local volume of the universe, a significant fraction of the expected normal matter is still missing. This is a profound revelation. The shortfall is not just a distant cosmological puzzle about the early universe. It is a present-day accounting issue right in our galactic neighborhood. The missing material is not hiding in some far-off, exotic corner of the cosmos. It is absent from the balance sheet of our local cosmic group and its surroundings. This points overwhelmingly to a single conclusion. The warm, hot intergalactic medium is not just a feature of the vast, ancient cosmic web. It is a pervasive, fundamental component of space itself, threading through even our local intergalactic environment. The filaments of the web are everywhere, and their hot, diffuse gas must account for that local shortfall. Our own local group, the small cluster of galaxies including the Milky Way and Andromeda, is floating within this invisible, seething ocean. When we weigh the total mass of our local group, most of it is the mysterious dark matter that provides the gravitational glue. But of the normal matter portion, a substantial amount is simply not in a form we can easily see with traditional telescopes. It is in the faint million-degree haze that fills the space between our galaxy and Andromeda, and in the even larger scale filaments that connect our local group to the Great Virgo cluster and beyond. The ghost is not just out there, it is right here, the hidden atmosphere of our local cosmic archipelago. This realization transforms the search from a grand cosmological quest into a personal one, challenging us to see what has been invisibly enveloping our home galaxy for billions of years. Magnetism adds a hidden force to this cosmic seascape. While we have mapped the hot gas and traced its distribution, another invisible player may be shaping its very behavior: cosmic magnetic fields. These are not the simple bar magnets of a school experiment, but vast, diffuse fields woven through the fabric of space itself, generated by the motion of charged particles over billions of years. Theorists now believe these fields likely thread through the warm, hot intergalactic medium, adding a crucial layer of complexity to our detective story. Imagine stirring a cup of hot tea. The heat spreads evenly as the liquid swirls. Now imagine that tea is filled with invisible, thread-like structures that resist the flow, channeling the heat in specific directions and preventing it from mixing smoothly. That is what magnetic fields could be doing within the WHIM. They can suppress certain processes, like thermal conduction, the normal way heat spreads from hotter regions to cooler ones. This means the gas within a filament might not be at a uniform temperature, but could contain pockets of varying heat, stabilized by these magnetic threads. Furthermore, these fields can influence the alignment of charged particles and even affect how light, particularly certain polarizations, travels through the medium. This magnetic fingerprint could subtly change the signals we are trying so hard to detect, whether it is the precise shape of an X-ray absorption line or the dispersion of a fast radio burst. It means our models, which often treat the WHIM as a simple, unmagnetized fluid, might be missing a key ingredient. Finding direct evidence of these large-scale intergalactic magnetic fields is extraordinarily difficult, but it is the next frontier. If confirmed, it would mean the missing baryons are not just floating in a hot, passive fog. They are part of a dynamic, magnetized plasma, a cosmic medium with its own hidden structure and rules, making the final accounting of the universe's ordinary matter an even richer and more intricate puzzle to solve. The ghost is not just hot, it is a spectrum of heat. Our search has focused on the searing million-degree plasma, but the warm, hot intergalactic medium is far more complex than a single temperature. This brings us to clue 16, the challenge of temperature distribution. The WHIM is not a uniform fog. It is a vast cosmic ecosystem of gas spanning an astonishing range, from what astronomers call warm at around 10,000 Kelvin, up to the truly hot at 10 million Kelvin or more. That is a difference of 1,000-fold in thermal energy. Think of it like Earth's atmosphere. We do not have one single temperature from the ground to the edge of space. We have layers, the troposphere where we live, the stratosphere, the mesosphere, each with its own distinct thermal properties. The cosmic web has its own layered thermodynamics, dictated by where the gas lies within a filament, how close it is to a galaxy cluster, and what violent events have recently energized it. This complexity creates a fundamental problem for detection, because no single telescope can see the entire range. Each instrument is tuned to a specific window, sensitive only to gas at a particular temperature. Ultraviolet telescopes are excellent at spotting the warmer gas, around a few 100,000 degrees, by detecting the absorption lines of certain ions. Optical telescopes, through the Lyman alpha forest, probe the cooler end of the spectrum. Our X-ray observatories, like Chandra and Irisita, are blind to this warm gas but excel at seeing the glow and absorption from the truly hot plasma above 1,000,000 degrees. And radio telescopes, through the dispersion of fast radio bursts, measure the total column of all free electrons, regardless of temperature, giving us an integrated sum. This means each observation gives us only a partial snapshot, a slice of the thermal pie. To find all the missing baryons, we cannot rely on one method. We must become cosmic synthesizers, piecing together the fragmented views from ultraviolet, optical, X-ray, and radio eyes into one coherent picture. It is like trying to diagnose a patient by only looking at their X-ray, then only listening to their heart, then only testing their blood. Each test reveals a critical piece, but only together do they show the full health of the system. The true solution to the missing baryon problem requires this complete medical chart of the cosmic web, proving that the missing mass is not in one place or one state, but distributed across a vast and dynamic thermal landscape that we are only now learning to map in its entirety. The scattered pieces of the thermal puzzle demand a new kind of instrument, one designed from the ground up to see the ghost in its entirety. This is the promise of Clue 17, the Athena X-ray Observatory. Slated for launch by the European Space Agency in the mid-2030s, Athena is not merely an upgrade, it is a paradigm shift. Imagine our current X-ray telescopes as keen-eyed observers squinting at a distant, fog-shrouded mountain range. They can make out the largest peaks and guess at the shapes of the valleys. Athena will be like stepping onto that range with a high-definition thermal camera and a laboratory-grade spectrometer, seeing every ridge, measuring the temperature of every stream, and analyzing the chemical composition of the very air. Its revolutionary leap comes from two key capabilities: an unprecedented sensitivity and a spectral resolution over 10 times sharper than today's best X-ray telescopes. This combination is tailor-made for the hunt. Athena's wide field of view and powerful optics will allow it to take exquisitely detailed X-ray spectra of not just a handful, but hundreds of quasars in a single observation. Each spectrum will be a forensic report, revealing not just the presence of highly ionized oxygen or neon in the warm, hot intergalactic medium, but its precise temperature, density, and velocity along that specific line of sight. It will see the faintest filaments, map their structure, and distinguish between different thermal phases of the gas with a clarity we can only dream of today. This mission is poised to deliver the first definitive, quantitative census of the hot baryons in the cosmic web. It will move us from the era of detective work and statistical hints into the age of precision cosmology, where we can finally weigh the invisible oceans with confidence and close the ledger on the missing matter problem for good. Athena represents the culmination of decades of theoretical prediction and technological ingenuity, a spacecraft built with one explicit goal: to finally look the universe's hidden skeleton in the eye and account for every last atom. The hunt for the missing atoms has focused on a searing, invisible fog, but perhaps we have been looking for a ghost that glows just a little. Another compelling possibility suggests some of the baryons are hiding in a slightly cooler, more tangible state, known as line-emitting gas. This is not the fully ionized plasma of the warm, hot intergalactic medium, but a warm phase where atoms have managed to hold onto a few more of their electrons. At these lower temperatures, tens of thousands of degrees instead of millions, specific elements like triply ionized carbon or silicon produce distinct, sharp emission lines in the ultraviolet part of the spectrum. Think of it like the difference between the uniform, blinding glow of a welder's torch and the specific, colored light of a neon sign. The WHIM is that overwhelming, broad blaze, while line-emitting gas is the neon sign, broadcasting its presence with a precise, though incredibly faint, color signature. The challenge is that this ultraviolet glow from cosmic filaments is so feeble it drowns in the background light of the universe. To find it, astronomers must perform the ultimate feat of contrast enhancement, targeting the dark regions between clusters where the signal might peek through. It is a search for the universe's hidden neon graffiti, subtle tags left on the vast pillars of the cosmic web. This approach offers a crucial complementary path. If the WHIM is the hot, diffuse ocean, then line-emitting gas represents the warm currents and streams within it, a different phase of the same hidden reservoir. Finding this emission would not only recover more missing baryons, it would paint a more complete picture of the thermodynamic life within the filaments, showing us where the hot plasma cools and condenses, perhaps on its long journey to someday fuel a new generation of galaxies. Beyond light and heat, the universe is threaded with bullets of pure energy. Cosmic rays, atomic nuclei accelerated to nearly the speed of light, constantly bombard our planet from deep space. Their origins are a mystery tied to supernova remnants and active galaxies, but their journey holds a secret for our search. As these ultra-high energy particles race across the cosmos, they do not travel alone. They pass through the diffuse seas of the warm, hot intergalactic medium, and here, a subtle interaction occurs. When a proton from a cosmic ray collides with a proton in the hot, tenuous gas of a filament, they can produce a fleeting, unstable particle called a pion, which almost instantly decays into gamma rays. This process is incredibly rare given the vast emptiness of space, but across the entire cosmic web and over billions of years, it could add up to a faint, diffuse glow. This is Clue 19, cosmic ray transport, a way to sense the ghost by the faint sparks it creates when invisible bullets strike invisible walls. The key is correlation. If this gamma ray signal exists, it should not be uniform across the sky. It should trace the same underlying architecture as everything else, glowing ever so slightly brighter along the dense spines of the cosmic web mapped by surveys like BOSS. Our best tool for this search is the Fermi Gamma Ray Space Telescope, which has spent over a decade meticulously scanning the entire sky for gamma ray sources. Astronomers are now sifting through Fermi's immense catalog of data, subtracting the brilliant point sources like pulsars and distant blazars to see what remains in the faint background. They are looking for a specific pattern, a whisper of excess gamma ray light that aligns with the known positions of galaxy clusters and filaments. It is an extraordinarily difficult task, like trying to hear a single, consistent hum in a stadium where everyone is shouting at once. But a positive detection would be revolutionary. It would provide a completely independent line of evidence for the WHIM, one based not on absorbed or emitted light from the gas itself, but on the energetic particles passing through it. It would tell us not just where the missing baryons are, but something about the dynamic environment they inhabit, a place traversed by the universe's most powerful natural accelerators. Finding this correlated glow would mean the cosmic web is not a passive reservoir. It is an active component in the grand cycle of matter and energy, a canvas upon which the universe's most violent events paint their faintest signature. This ghostly ocean is more than a cosmic reservoir. It is the very stage upon which galaxies are born and struggle to survive. The location and state of these missing baryons are not a side mystery. They are a central plot point in the story of cosmic evolution. If the majority of normal matter is indeed spread across a hot, diffuse web, then galaxies face a constant uphill battle. To grow, to form new stars, they must pull this material in from the vast intergalactic wilderness. But that is incredibly difficult to do. Imagine trying to gather steam from a sauna with a butterfly net. The gas in the warm, hot intergalactic medium is so energetic, so hot, that it easily overcomes the gravitational pull of an average galaxy. It simply will not cool down and condense easily. This creates a cosmic bottleneck, regulating the pace of star formation across the universe. The most massive galaxy clusters, with their immense gravitational wells, are the only entities strong enough to capture and hold onto this hot plasma, which is why we see those colossal X-ray halos. But for smaller galaxies like our Milky Way, the web is a tantalizing yet stubborn supplier. The baryons are there all around us, but they are in a form that is frustratingly hard to collect. This transforms our understanding of galaxy growth. It is not a simple story of gas falling smoothly into a waiting disk. It is a dynamic, often violent tug of war. Galactic winds from supernova blow material out, while the gravity of the galaxy and its dark matter halo tries to pull gas in from the web. The circumgalactic medium is the turbulent front line of this battle, a place of constant recycling where hot gas might finally cool, or where cool gas might be reheated and ejected. The solution to the missing baryon problem therefore unlocks a deeper truth. It explains why the universe is not brimming with far more stars than we see. The very structure of the cosmos, with its hot filamentary web, acts as a cosmic thermostat, keeping most of the fuel locked in a state that is difficult to use, ensuring that galaxies grow slowly and deliberately over billions of years. Our own Milky Way's history, its periods of star formation and quiescence, is written in the ebb and flow of this hidden, hot sea. One of the most profound puzzles in modern cosmology is the Hubble tension. We have two supremely precise ways to measure how fast the universe is expanding, a number called the Hubble constant. One method uses the cosmic microwave background, the ancient afterglow, to predict what the expansion rate should be today. The other uses a cosmic distance ladder, observing stars and supernova in the nearby universe to measure the rate directly. These two methods, both exquisitely refined, do not agree. They differ by a small but stubborn amount, suggesting a fundamental gap in our understanding of cosmic evolution. This is where our two great mysteries might whisper to each other. Could the missing baryons, and the specific way they are woven into the warm, hot intergalactic medium, hold a clue to this discrepancy? It is a compelling, though speculative, thought. The standard model of cosmology assumes that dark energy, the force accelerating the expansion, is a constant, uniform property of space. But what if it is not so simple? Some theorists propose that if a portion of the missing baryons exist in a slightly different form, or if they interact in subtle ways with dark matter or dark energy across cosmic time, it could have gently altered the expansion history of the universe. A small tweak to that history could, in principle, bring the two measurements of the Hubble constant into alignment. Imagine the cosmic web not just as a reservoir of hot gas, but as an active component with its own evolving influence on the fabric of space. Perhaps the process of heating this vast ocean of matter through eons of galactic winds and black hole feedback injected a tiny amount of extra energy into the cosmos at a specific era, subtly changing how fast space stretched. Or maybe the distribution of the WHIM itself affects how we measure distances on the largest scales, creating a cosmic mirage that skews our observations. This connection remains unproven, a tantalizing hypothesis at the frontier of cosmology. Yet it underscores a powerful idea. Solving the missing baryon problem is not just about balancing a ledger. It could be the key that unlocks a deeper layer of cosmic physics, revealing that the ordinary atoms we have been searching for are entwined with the universe's most profound mysteries. Finding them might not just tell us where the matter went, but how the very stage of reality has been expanding beneath our feet all along. The universe's hidden architecture is shaped by an invisible hand, but even gravity's blueprint depends on who is in the room. Among the most elusive residents are neutrinos, ghostly particles that stream through you by the trillions every second. They are not baryons, not the missing matter we seek, but they hold a subtle, crucial power over the entire search. Born in the nuclear furnaces of stars and the cataclysmic violence of the Big Bang, neutrinos are almost massless, chargeless, and famously indifferent to normal matter, passing through entire planets as if they were empty space. Yet, they are not completely weightless. Their exact mass remains one of physics' great unsolved puzzles, and this tiny bit of heft, multiplied across the uncountable trillions permeating every cubic inch of the cosmos, adds up to a significant gravitational influence over cosmic time. This is Clue 22, the role of neutrinos. To understand why this matters for finding missing baryons, think of the cosmic web as a sculpture shaped by gravity pulling on all forms of mass, both dark and visible. Our supercomputer simulations, the treasure maps guiding our telescopes, must account for every source of that gravitational tug. If we get the neutrino mass wrong, the simulation's prediction for where the dark matter filaments form will be slightly off. And since the warm, hot, intergalactic medium follows those dark matter threads like water following a riverbed, our prediction for where to find the hot baryons will be off too. It is a cascade of cosmic precision. A neutrino mass that is too high would mean these particles were more influential in the early universe, smoothing out the formation of small-scale structures and potentially altering the final pattern of the web we see today. A mass that is too low might mean our models are missing a key piece of gravitational glue. Getting this number right is not an academic exercise. It is essential calibration for our entire search operation. Experiments deep underground, like the Karlsruhe tritium neutrino experiment in Germany, are inching closer to measuring the absolute neutrino mass. Their answer will be fed directly into the next generation of cosmic simulations, sharpening the digital map of the web and telling our telescopes with even greater accuracy where to point to finally weigh the ghost. The lightest things in creation, it seems, hold the key to finding some of the heaviest. Precision mapping demands an unprecedented view of the sky, and a new giant is about to open its eye. The Legacy Survey of Space and Time, conducted by the Vera C. Rubin Observatory in Chile, represents a fundamental shift in scale. For 10 years, its immense mirror and gargantuan camera will scan the entire southern sky every few nights, not once, but over and over, compiling a cinematic record of the cosmos. It will catalog tens of billions of galaxies, spotting objects 100 million times fainter than the human eye can see. For our search, this is not about looking at the hot gas directly. The LSSD power lies in its ability to map the invisible scaffolding with staggering precision. By tracking the subtle distortions in the shapes of those billions of galaxies, an effect called weak gravitational lensing, the survey will infer the distribution of dark matter across the universe. It will produce the most detailed, three-dimensional chart of the cosmic web's skeleton ever created, a map of the gravitational riverbeds where all matter flows. This map will be a game-changer for WHIM hunters. Currently, surveys like BOSS gave us a good outline, but the LSSD will provide a high-definition blueprint. It will identify the faintest, most tenuous filaments with exquisite clarity, telling telescopes like Athena and the next generation of X-ray observatories exactly where to aim their precious observing time. It creates a powerful synergy, a division of labor on a cosmic scale. The Rubin Observatory finds the bones, and other telescopes probe the hot blood flowing through them. This collaborative future turns the hunt into a coordinated scientific campaign, moving from isolated detective work to a full-scale forensic investigation of the universe's hidden anatomy. The ghost can run, but soon it will have nowhere left to hide. This ghost cannot be caught by any single hunter. The final clues demand a symphony of perspectives, a revolution in how we perceive the cosmos itself. This is Clue 24, the multi-messenger astronomy revolution. For decades, we have been like astronomers with a single, narrow-band radio, trying to understand a concert by listening to only the bass line. We heard a deep rumble but missed the melody, the harmony, the percussion. To solve the Missing Baryon mystery, we must now listen to the entire cosmic orchestra, across every frequency and through every possible medium. It means correlating data from radio telescopes that catch the smeared chirps of fast radio bursts, with ultraviolet observatories that see the warm glow of line-emitting gas, with optical surveys that map the galaxy-studded filaments, and with X-ray eyes like Chandra and Irisita that see the searing plasma. Each instrument hears a different section of the orchestra. The radio data gives us the total electron count, the base note of mass. The ultraviolet reveals the warmer currents, the mid-range melody. The optical surveys provide the sheet music, the structure of the cosmic web itself. The X-rays deliver the blistering heat of the high notes, the screaming violins of million-degree plasma. Only when we synchronize all these signals do we hear the full composition. And the revolution goes beyond light. We are now incorporating cosmic messengers that are not photons at all, like the potential gamma ray glow from cosmic ray interactions, or even the faint gravitational influence of the filaments themselves on the motion of galaxies. Imagine a graphic, not of one telescope, but of a dozen different eyes in space and on the ground, all trained on the same faint thread of the cosmic web. A radio dish, an optical telescope, an X-ray observatory, and a gamma-ray detector, their data streams merging into a single, coherent portrait. This is the 21st century attack on the problem, a coordinated, multi-pronged assault that treats the universe not as a collection of isolated phenomena, but as an interconnected physical system. We are no longer just astronomers. We are cosmic synthesists, weaving together every whisper and shout from the void to finally understand the hidden anatomy of everything. The hunt for the missing half of creation is more than a scientific ledger. It is a fundamental redefinition of what it means to see. For millennia, our understanding of the cosmos was limited to what our eyes, and later our optical telescopes, could capture, the pinpricks of stars and the smudges of galaxies. We mapped a universe of light, but this entire pursuit has revealed a profound truth. Most of the universe's normal matter does not glow for us. It exists in a state of radiant darkness, a hot, diffuse medium that is essentially invisible to our traditional senses. To find it, we had to learn to see with new eyes, to interpret shadows on ancient light, to decode faint whispers in X-ray spectra, and to measure the smear of a millisecond radio chirp. Clue 25 is not about another telescope or a new particle. It is the philosophical implication of seeing the unseeable. This entire journey celebrates a different kind of vision, one built on human ingenuity, indirect inference, and relentless curiosity. Astronomers did not find the missing baryons by looking directly at them. They found them by reading the subtle distortions they imprint on everything else. They used the universe itself as a laboratory, employing quasars as backlights, the cosmic microwave background as a canvas, and fast radio bursts as cosmic dipsticks. It is detective work on the grandest scale, where the crime scene is all of space and time, and the clues are immeasurably faint signatures hidden in a sea of noise. This achievement underscores a powerful idea about our place in the cosmos. We are not passive observers of a finished spectacle. We are active participants in an ongoing discovery, using our minds and our machines to peel back layer after layer of reality, each more subtle and astonishing than the last. Finding the missing baryons means we have finally begun to perceive the universe's hidden architecture, the hot, flowing skeleton that has been there all along, holding the galaxies apart and dictating the slow, grand rhythm of cosmic evolution. It transforms our map of the cosmos from a sketch of isolated islands to a dynamic portrait of an interconnected web, with our own galaxy adrift in a vast, invisible ocean we have only just learned to measure. The story closes not with an ending, but with a new beginning, a deeper, richer understanding that the true nature of reality is often hidden in plain sight, waiting for the right combination of questions, tools, and human imagination to bring it into view. So the cosmic ledger is finally beginning to balance. We began with a staggering 50% deficit, a universe that seemed to have lost half its ordinary atoms between the afterglow of the Big Bang and the galaxies we see today. This was the opening clue, a cosmic census discrepancy that launched the greatest detective story in modern astronomy. We followed the evidence to a prime suspect, the warm, hot intergalactic medium, a ghostly ocean of million-degree gas woven into the filaments of the cosmic web. To see this invisible architecture, we had to invent new ways of seeing, from X-ray eyes tracing faint glows, to using quasars as cosmic backlights, to reading the subtle shadows cast on the oldest light in existence. We learned to listen for the dispersed chirps of fast radio bursts, acting as perfect dipsticks for the hidden seas. We mapped the web's skeleton with galaxy surveys and supercomputer simulations, then hunted within it for the chemical fingerprints of highly ionized oxygen, the smoking gun. We discovered that galaxies themselves, through furious winds and black hole eruptions, are the pumps that fill this vast reservoir, and that our own Milky Way floats within its local expanse. Each clue, from the Sunyaev-Zel'dovich effect to the promise of multi-messenger astronomy, represents a triumph of indirect inference, a way to perceive the unseeable by the delicate imprint it leaves on everything else. While the case is not yet fully closed, the evidence is converging with remarkable power. The overwhelming consensus is that we have found where the missing baryons have been hiding all along, not in some exotic form, but as a hot, diffuse plasma tracing the grand design of the cosmos. The final verdict now awaits a new generation of explorers. Upcoming missions, like the Athena X-ray Observatory, are poised to deliver that definitive census, to weigh the ghost with precision and settle the ledger for good. This journey reminds us that the universe's greatest secrets are often hidden in plain sight, written in a language of faint whispers and subtle shadows. It invites us to stay endlessly curious, to look beyond the stars and wonder about the hidden structures that cradle them. Which of these 25 clues did you find most fascinating? Was it the idea of fast radio bursts as cosmic dipsticks, or the galactic superwinds painting the web with exiled atoms? Share your thoughts below, and if you enjoyed this cosmic detective story, consider subscribing for more journeys into the hidden layers of reality.